Okay, picture this. You're fumbling for a flashlight during a blackout, right? Or maybe you're frantically plugging in your phone, watching that battery icon just disappear.
We've all been there.
Exactly. And what's the invisible force behind all that? Electricity. It runs, well, pretty much everything these days.
It really does. And today, we're not just going to take it for granted. We're doing a deep dive using the sources you sent over, all about current electricity.
Yeah, think of this as like your personal guide to understanding what's actually going on.
We want to give you a real solid grasp of this fundamental concept.
Right. And these sources look pretty good. Seems like solid educational stuff that, breaks down the complex bits.
Yeah, they seem designed to make things click.
So our mission here is to pull out the key ideas about current electricity. Everything from like the basic building blocks all the way to how we can use energy smarter.
We're aiming for those moments where it just clicks, those aha insights that really make sense and stick with you.
Okay, so what's the plan? How are we going to tackle this?
Well, first, we'll look at where direct current actually comes from. You know, those little power packs we call cells?
Okay, cells. Got it.
Then we'll try to demystify what electric current really is, that whole flow of charge thing. We'll also cover the basic parts of circuits using their standard symbols, the visual language, basically.
Right, the diagrams.
Exactly. And get a handle on potential difference in resistance. And finally, tie it all together with, the really practical side, using energy efficiently.
Sounds like a good roadmap.
Yeah.
Let's dive right in then. Sources of direct current, like those batteries in a flashlight you mentioned. Cells.
Yep, those are the classic example. They provide direct current, or DC.
And direct current means?
It means it's a steady flow. The electrical charge moves consistently, doesn't really change in strength, and always goes in the same direction. Think of it like water flowing smoothly one way down a pipe.
Okay, steady in one way. And these cells, like a standard AA battery, they're doing something pretty cool inside, right?
They are. They're basically little chemical energy converters. They transform stored chemical energy into electrical energy we can use.
And, the little bump on top, the brass cap,
Yeah.
that's usually the positive end.
That's right. And the flat bottom, or the casing, often zinc, is the negative terminal.
So what's actually in the cell that makes this happen?
At a basic level, you've got two different conductive materials. Those are the electrodes, and they're sitting in or separated by a substance called the electrolyte. That whole setup allows the chemical reactions to happen that, push the electrons out and create that electrical energy.
Okay. Now, the sources mentioned different types of cells, primary and secondary. What's the deal there?
Yeah. The key difference is really about the chemistry inside specifically, whether the chemical reaction can be reversed.
Okay.
Primary cells use irreversible reactions. Once the chemicals are used up, that's it. The cell is done, disposable.
Like your typical alkaline battery. Use it till it's dead, then toss it.
Exactly. Examples include those older ones like voltaic, Leclanche cells, the Daniell cell, and the common dry cell.
Okay, irreversible. Then secondary cells must be.
Reversible. They're also called accumulators. These use chemical reactions that can be reversed.
So you can recharge them.
Precisely. When you charge them, you feed electrical energy back in, which reverses the chemical process, storing energy chemically again. Then, when you use it, it converts that chemical energy back to electrical.
Like the battery in my phone or laptop?
Exactly. Or the lead-acid battery in a car, nickel-iron ones, and the lithium-ion batteries that power most of our portable gadgets now. They're all secondary cells.
Rechargeable, that makes a huge difference, obviously. Convenience, less waste.
Definitely. So primary is a one-way street for energy. Secondary is like a round trip.
Is there a trade-off, performance-wise?
Yeah, there often is. Primary cells sometimes have a bit more, let's call it internal resistance, kind of like internal friction. They might struggle a bit more under a heavy load compared to secondary cells. Secondary cells, like your phone battery, generally have lower internal resistance, so they can deliver power more smoothly, especially for high current tasks.
So primary for low power things like remote controls maybe, secondary for phones, cars.
That's a good rule of thumb. Also, primaries are usually lighter and cheaper up front, but you keep buying them. Secondaries cost more initially and can be heavier, but you recharge them hundreds, maybe thousands of times, so long-term savings and less environmental impact.
Right. Different tools for different jobs. Makes sense. Okay, so that covers where the current comes from. Now, what is current, fundamentally? Sources say it's the flow of charge.
That's the core idea. Remember static electricity, rubbing things, transferring charge temporarily?
Yeah, like rubbing a balloon on your hair.
Right. Well, electric current is like that. but continuous. It's the rate at which electric charge flows past a certain point or across a specific area.
A rate. So like how much charge flows per second.
Exactly. We write it as I OQT. Current I is the amount of charge Q divided by the time T it takes to flow.
ITT.
Got it. And technically, current itself is a scalar, just a magnitude. We talk about its direction in a circuit, but the quantity itself isn't a vector.
Okay, so what's actually doing the flowing? What's carrying the charge?
Depends on the material. In metals, like copper wires, it's electrons, those tiny negative particles whizzing around. In electrolytes, like the stuff inside some batteries or solutions, it's actually ions moving. Both positive and negative ions can be carrying the charge.
Ions. Charged atoms or molecules.
Right. And just for scale, one single electron carries a minuscule negative charge, about 1.6 times 10 to the minus 19 coulombs. Incredibly tiny.
Wow, so even a small current must mean billions and billions of electrons moving.
Oh, absolutely. Astronomical numbers. If you have n electrons flowing past a point in time t, the total charge Q is just n times the charge of one electron, E, Q net.
Okay.
So the current, I Q T, becomes I N net. Think about it. To light even a tiny LED, you've got trillions upon trillions of electrons moving every second.
That's mind-blowing. And in those electrolytes, with positive and negative ions going opposite ways, how does that work for current?
That's interesting. If you have, say, N1 positive ions, charge Q1 moving one way, and N2 negative ions, charge Q2 moving the opposite way in the same time.
Yeah.
The total current is actually the sum of the charge flows from both, because a negative charge moving left is effectively the same as a positive charge moving right in terms of overall current direction.
Oh, okay. So their effects add up because of the direction convention.
Exactly. Which brings us to that classic point of confusion, conventional current versus electron flow.
Right. I remember this being tricky. Can you clarify that one more time?
Sure. So way back when, before they knew electrons were the main charge carriers in metals, scientists just sort of guessed. They assumed the current flowed from the positive side to the negative side.
Okay, positive to negative.
And that idea stuck. We call it conventional current, but now we know that in metals, it's the negatively charged electrons that are actually moving.
And they're repelled by the negative terminal and attracted to the positive one.
Exactly. So the electrons actually flow from negative to positive, the opposite direction to conventional current.
So why do we still use the old way?
Mostly history and convenience. All the formulas, the circuit analysis techniques, they were built around the positive to negative idea. And honestly, it works perfectly well for calculations. The math comes out the same.
Huh. Okay, so conventional current, positive to negative, is the standard for diagrams in math, even if the electrons are actually going the other way, negative to positive, in the wires.
You got it. It's like an agreed upon standard, a useful fiction in a way. Just have to remember which one you're talking about.
Definitely a key point. Okay, so how do we measure this flow? What's the unit for current?
The standard unit is the ampere, named after Andrea Marie Ampere. We just call it the amp, symbol A.
Amp, okay. And what does 1 amp mean?
1 amp means 1 coulomb of charge is flowing past a point every second. 1 A is 1 C's. That's the definition.
1 coulomb per second. And a coulomb is how many electrons again?
A huge number. About 6.25 times 10 to the power of 18 electrons.
Whoa.
So a current of just 1 amp means 6.25 quintillion electrons are streaming past a point in that wire every single second.
Okay, that really puts it into perspective. Just incredible numbers. And what if the current is really small?
We use prefixes. Milliamps, MA, for thousandths of an amp, and microamps for millionths of an amp. You see those in electronics a lot.
Right, for delicate circuits. Okay, we've got the source, cells, what current is, flow of charge, and how we measure it, amps. Now, let's talk about drawing this stuff, circuit diagrams and symbols.
Yeah, absolutely essential. Instead of drawing a realistic picture of a battery and a bulb and wires, which would get messy fast, we use a standard set of symbols. It's like a universal language for electricity. Makes diagrams clean, clear, and easy for anyone to understand.
Like a schematic. Okay, so what are the key symbols? We talked about cells and batteries.
Right. A single cell is 2 parallel lines, one longer and thicker, that's the positive terminal, often marked plus, and one shorter and thinner, the negative, maybe marked him.
Long is positive, short is negative.
Got it. A battery is just several of those cell symbols strung together, end to end, usually positive to negative.
Makes sense. Multiple cells. What about AC power, like from a wall outlet?
That's usually a circle with a little wavy line inside, like a sine wave, because the current alternates direction.
Okay, and the things that turn circuits on and off?
Yep.
Switches, Keys?
Yep, they control the flow by making or breaking the connection. A simple switch might look like a little drawbridge, a line that's either angled up, open, no connection, or down touching the circuit line, closed, connection made.
Open and closed.
A plug key symbol often uses brackets. Open
Yeah.
is like closed is a tapping key for brief connections, looks slightly different but does the same job momentarily. The point is showing whether the path is complete or broken.
Right. Now, what about controlling how much current flows? Resistance.
Ah, yes. A fixed resistor, like a piece of resistance wire,
Yeah.
is usually shown as a zigzag line.
Okay, the zigzag.
But often you want to vary the resistance. That's where a rheostat comes in.
A rheostat. How's that shown?
It's usually the zigzag symbol again, but with an arrow going through it or pointing to it to show it's adjustable with an arrow.
Arrow means variable.
Exactly. Rheostats often have 3 connection points, say A, B, and C. S and B are the ends of the whole zigzag wire, so connecting there gives you the full fixed resistance.
Uh-huh.
Terminal C is connected to a slider, a jockey, that moves along the zigzag wire. So if you connect between C and, say, A, then moving the slider changes the length of the wire in the circuit.
Oh, I see. So you change the effective length, and that changes the resistance.
Precisely. More length, more resistance, less length, less resistance. It gives you continuous control.
That's clever. What about a resistance box?
That's different. It usually contains precise, fixed resistors inside. The symbol is often just a rectangle. You choose the resistance value by removing specific plugs, adding those fixed resistances into the circuit. Not continuous like a rheostat, but gives you known values.
Okay, rheostat for continuous, box for specific values. Got it. Now, the measuring tools. Ammeters and voltmeters.
Right. An ammeter measures current amps. Its symbol is a circle with an A inside.
Circle A. How do you connect it?
Always in series with whatever you're measuring the current through. The current has to flow through the ammeter.
In the main path?
Yep. And you have to connect the plus terminal of the ammeter towards the positive side of the power source. Importantly, ammeters are designed to have very, very low resistance themselves, so they don't mess up the current they're trying to measure.
Low resistance, connect in series.
Okay.
Voltmeter.
Measures potential difference, or voltage, volts. Symbol is a circle with a V inside.
Circle V connection.
Always in parallel across the component you want to measure the voltage of. You connect it across 2 points.
Across the component, not in the main line.
Right, like probing 2 points. It also has a plus terminal that goes towards the positive side. And crucially, voltmeters are designed to have very, very high resistance.
High resistance. Why?
So that very little current flows through the voltmeter itself. You want it to measure the voltage without drawing significant current away from the circuit it's measuring.
Okay. Ammeter, low resistance, series. Voltmeter, high resistance, parallel. That's a key difference. What about a galvanometer?
Symbol is a circle with a G. G. It's basically a very sensitive detector for small currents.
Sensitive detector.
Yeah, and it usually shows the direction too. The needle starts in the middle, 0, and deflects left or right depending on which way the tiny current is flowing.
Right.
Like an ammeter, you connect it in series.
Yeah.
It doesn't usually have polarity markings because it can read either way.
Okay, detects small currents in direction. Finally, the things that actually use the electricity. The load.
Right, the appliance or component doing the work. A light bulb symbol is often a circle with a cross inside, X, or maybe a little loop representing the filament. A heater might just be the resistor zigzag symbol, sometimes in a circle, sometimes just R for a generic load or resistance.
Okay, and the wires connecting everything.
Just simple straight lines. They represent the conducting paths, assumed to have negligible resistance themselves, usually copper or aluminum.
Lines of wires.
Got it.
Got it. Okay, we have the parts list, the symbols. Let's build some circuits.
Let's start simple. Think about that flashlight again. What's in there?
Batteries, cells, a light bulb, and a switch.
Exactly. That's a basic series circuit. The cell, switch, and bulb are connected one after another in a single loop.
Series means one path.
Right. When you slide the switch on, you close the circuit, you complete the path. Current flows from the positive end of the cell through the switch, through the bulb's filament,
Making it glow.
making it hot and glow, and then back to the negative end of the cell. Open the switch, you break the path, current stops, bulb goes off. Simple.
Okay, that makes sense. What about something a bit more elaborate, using more of those symbols?
Okay, let's imagine a circuit. We have a cell, a key, switch, then maybe a rheostat, then a bulb, our load. Let's also put an ammeter in series with the bulb and rheostat.
Okay, cell, key, rheostat, bulb, ammeter, all in a line.
Yep, all in series. Now let's connect a voltmeter in parallel just across the bulb.
So the voltmeter is connected to the points just before and just after the bulb.
Exactly, measuring the voltage drop across the bulb.
Okay, got the picture. What happens now?
Well, first, if the key is open,
No complete circuit.
right, so no current flows. Bulb is off, ammeter reads 0, voltmeter reads 0, everything's dead.
Makes sense. Now close the key.
Click, circuit complete. Now current flows from the cell through the key, rheostat, bulb, ammeter, and back.
So the bulb lights up?
Yep, and the ammeter shows a reading that's the current flowing through the circuit. The voltmeter also shows a reading that's the potential difference across the bulb.
Okay, things are working. Now what about that rheostat? We can adjust it, right?
Yes, that's the cool part. Let's say we slide the contact on the rheostat to increase its resistance.
Making it harder for current to flow.
Exactly. So what would you expect to happen?
Less current, so the ammeter reading would go down.
Yeah.
And maybe the bulb gets dimmer.
Perfect. Less current flows through the whole series circuit. The bulb glows dimmer, the ammeter reading drops. And usually, the voltmeter reading across the bulb will also drop because less current is flowing through the bulb's fixed resistance.
And we decrease the rheostat's resistance.
Opposite effect. Easier path for current. More current flows, ammeter reading goes up, bulb gets brighter, voltmeter reading across the bulb goes up.
Ah, so the rheostat lets us control the brightness and the current. That demonstrates Ohm's law, right? VIR.
Beautifully. It shows how changing resistance affects current and voltage in a real circuit, and it reinforces series connections, same current through all, and parallel voltmeter measuring voltage across one part.
Okay, that circuit example really pulls it together. Now let's talk about the materials themselves, insulators and conductors.
Right, fundamental difference. Insulators are materials that just don't really let electric current flow through them easily or at all because their electrons are held very tightly by their atoms. There aren't many free electrons available to move and carry charge, so they have very high resistance.
Like the plastic coating on wires.
Exactly. Plastic, rubber, glass, wood, cotton, paper, even pure water. They're all insulators. They keep the electricity where it's supposed to be.
Prevents shocks and shorts. Okay. Conductors.
They're the opposite. They let current flow easily because they have lots of free electrons, electrons that aren't tightly bound and can move pretty freely through the material when you apply an electric field, like a voltage. So they have low resistance.
Metals, mostly.
Metals are the classic conductors. Copper, aluminum, silver, iron, steel, brass. They're all excellent. But also impure water, with dissolved salts or minerals creating ions, mercury, and even the human body, unfortunately, can conduct electricity.
Right, which is why electrical safety is so important.
Right.
So it's all about those free charge carriers, electrons in metals, ions in liquids.
That's the key distinction, and this leads directly to the idea of open versus closed circuits.
We touched on this. Closed circuit means
A complete unbroken path made of conducting material. It forms a loop from the power source through the components and back again. Current can flow continuously.
like a closed loop,
Yep. An open circuit is where that path is broken. There's a gap,
like an open switch.
or a broken wire, or maybe even a piece of insulating material inserted into the path. If the loop isn't complete, the current can't make the round trip. No continuous flow.
Closed circuit, current flows. Open circuit, current stops. Got it. Okay, let's dig into the why behind the flow. Potential difference and resistance, the driving force and the opposition.
Right. Think about two metal objects. If one has way more electrons than the other, and you connect them with a wire.
Electrons will flow from the one with more to the one with fewer.
Exactly. They flow to try and even things out, moving from higher electron concentration, more negative, to lower concentration, less negative or positive. It's like air moving from high pressure to low pressure.
Okay, they want to balance out. But in a circuit, the flow keeps going. How?
That's the job of the cell or battery. It acts like an electron pump.
A pump.
Yeah. Through its chemical reactions, it constantly works to pull electrons away from one terminal, making it positive, the anode, and pile them up on the other terminal, making it negative, the cathode.
So it maintains the imbalance.
Precisely. It maintains that difference in electron concentration, which creates an electrical pressure difference. We call that potential difference. It uses chemical energy to keep that potential difference across its terminals.
So the cell provides the continuous push. You mentioned analogies earlier.
Yeah.
Like water pressure or height.
Yeah, they're helpful. Think of electric potential like height. Water naturally flows downhill from higher gravitational potential to lower. Similarly, charge tends to move because of a difference in electric potential. Or think of water pressure. Water flows from high pressure to low pressure in pipes. Electric potential difference is like the electrical pressure difference driving the flow.
So high potential means fewer electrons, positive charge.
Generally, yes. A region with a deficit of electrons is considered at a high potential positive. A region with an excess of electrons is at a low potential negative.
Okay, a high potential, positive-ish, low potential, negative-ish.
Right. Now remember, the electrons themselves, being negative, are actually pushed away from the low potential negative terminal and pulled towards the high potential positive terminal in the external circuit.
Ah, right. Electrons go low to high potential.
But the conventional current, the one we use in diagrams, flows the other way, from high potential to low potential.
Still feels backwards, but okay. Convention, high to low, electrons, low to high. Got it tattooed on my brain now.
Good. Now, moving these charges, especially if you're moving them against electric forces, like pushing positive charges together, takes work. It requires energy.
Like lifting something against gravity takes work.
Similar idea. This leads us to define potential difference more formally. The potential difference, often just called voltage, between 2 points, is the amount of work done per unit of charge to move that charge between those 2 points.
Work per charge, okay.
So V equals WQ. Potential difference. V equals work done, W, divided by the charge moved Q. It's a scalar quantity.
V equals a WQ. And the unit, you said volts before.
Yep, the volt,
Right.
V, named after Alessandro Volta. 1 volt is defined as 1 joule of work done per coulomb of charge moved. 1 V equals 1 JC.
So if it takes 1 joule of energy to move 1 coulomb between 2 points, the potential difference is 1 volt.
You got it. That's the electrical push.
Okay, what about the thing pushing back? Resistance.
Right. Electrical resistance is basically the opposition a material presents to the flow of that electric current. It's like friction for electricity.
Friction.
Right.
How does that work inside the wire?
Well, those free electrons we talked about aren't just zooming freely in a straight line. As they drift through the wire, driven by the potential difference, they're constantly bumping into things.
Bumping into what?
Into the fixed positive ions that make up the structure of the metal, and also bumping into other electrons. It's a chaotic, microscopic dance. These collisions slow them down, impede their overall progress.
So they don't just accelerate continuously.
No, they reach a kind of average drift speed because of all the collisions, and those collisions convert some of the electrical energy into heat. That's why wires get warm when current flows.
Ah, the collisions cause heat,
Yeah.
okay. And Ohm's law connects resistance to voltage and current.
Yes, the fundamental relationship. Ohm's law says that the current, I, through a conductor is directly proportional to the potential difference V across it, as long as things like temperature stay the same.
More push V, more flow I. Makes sense.
And the constant of proportionality is the resistance R. So V equals IR, or you can rearrange it. R equals VIR. Resistance is the ratio of voltage to current, also a scalar.
V equals IR, or R equals V over I. Got it. And the unit for resistance.
Is the ohm, named after Georg Ohm. The symbol is the Greek letter omega, A. Looks a bit like a horseshoe.
Omega, okay. And
Okay.
1 ohm means
1 ohm is the resistance of a conductor. When a potential difference of 1 volt across it causes a current of 1 ampere to flow through it. 1A equals 1V1A.
okay. So higher resistance means less current for the same voltage push.
Yeah.
Makes sense. What makes something have high or low resistance? What factors matter?
4 main things, usually. First, the material itself.
Like copper versus rubber.
Exactly. Different materials just inherently have different numbers of free electrons and different atomic structures, affecting how many collisions happen. Metals, low resistance. Insulators are very high resistance. That's kind of obvious.
Okay, material. What else?
Length. Resistance is directly proportional to the length of the conductor.
Longer wire, more resistance.
Yep. Think of it as a longer obstacle course for the electrons, more chances for collisions over a longer distance.
Okay, length. Third.
Cross-sectional area, how thick the wire is. Resistance is inversely proportional to the area.
Inversely, so thicker wire.
Means less resistance. Think of a wider pipe allowing more water flow. A thicker wire gives electrons more paths, more space to move, reducing the overall opposition.
Right. Thicker wire, less resistance. Makes sense for carrying large currents. And fourth.
Temperature. For most metallic conductors, resistance increases as temperature goes up.
Hotter wire equals more resistance. Why?
Because when the material gets hotter, the atoms and ions in the lattice vibrate more vigorously, more wildly.
Wow.
This increased vibration makes it even more likely that the drifting electrons will collide with them. More collisions mean more opposition to flow, hence higher resistance.
Okay, so material, length, longer, more, area, thicker, less, and temperature.
Yeah.
Hotter, more for most metals.
Got it.
Now let's switch gears a bit to something really important today. Efficient use of energy.
Hugely important. Energy efficiency is basically about getting the same job done, same comfort, same service, same product, but using less energy to do it.
Doing more with less energy.
Exactly. And the benefits are huge. It saves money, obviously, on energy bills. But critically, it also reduces our reliance on energy sources and cuts down on greenhouse gas emissions and other pollution associated with energy production. It's about using smarter technologies and processes.
What are some common examples we might see?
Well, in homes, good insulation is a big one.
Keeping heat in during winter, out during summer.
Precisely. Reduces the energy needed for heating and cooling. Using natural light, big windows, skylights cuts down on artificial lighting needs during the day.
And light bulbs themselves have improved massively.
Oh, definitely. Moving from old incandescent bulbs to compact fluorescents, CFLs, was a big step. CFLs used maybe 60–70% less energy.
I remember those twisty ones.
Yeah. But now, LED's light-emitting diodes are even better. They use drastically less energy than even CFLs for the same brightness, and they last incredibly long.
Plus no mercury like CFLs had, right?
Right. That's another environmental win. Switching to LEDs globally makes a massive difference in energy consumption and avoids that hazardous waste issue. It's a huge step.
And appliances too. Refrigerators, washing machines.
Absolutely. Look for those Energy Star ratings or similar labels. Modern appliances are designed to be way more efficient than older models, using less electricity and sometimes less water, too.
Even how buildings are designed.
Yes. Things like orienting a building to take advantage of the sun, placing windows strategically, using light-colored roofing materials to reflect heat. It all adds up to reduce the energy needed for lighting, heating, and cooling.
What about bigger scale? Industry, transportation.
Big potential there, too. Industries are using more efficient boilers and furnaces that use less fuel, developing processes that require less energy. In transport, cars are getting lighter, tires have less rolling resistance, engines are smarter, computer-controlled for better fuel economy.
And electric vehicles, of course.
EVs are a major part of it, shifting energy use away from gasoline, especially if the electricity comes from clean sources. It's all part of the push for greater efficiency.
It really sounds like these efforts, big and small, could make a real dent in global energy use.
They absolutely can. The International Energy Agency, the IEA, estimated that if we really deployed all the cost-effective efficiency measures we already have, we could potentially cut global energy demand by something like a third by 2050. A third! That's enormous. It's one of the most powerful tools we have to tackle climate change and ensure energy security.
Wow, a third. That's staggering. Which leads to the social side of this. How do we actually make this happen? Our sources mention social initiatives.
Right, because technology alone isn't enough. We're facing depleted resources, environmental impacts. We need to change how we think about and use energy.
So raising awareness is key.
Crucial. People need to understand why it matters and what they can do, making energy use less abstract, more tangible.
How do you do that effectively?
Well, mass media campaigns can help. Education is vital, especially starting young, getting energy conservation into schools, maybe through eco clubs or projects.
Instilling those habits early.
Exactly. And community involvement is powerful. When people see their neighbors making changes or local groups running initiatives, it creates momentum. Social norms shift.
Peer pressure in a good way.
Sort of. And NGOs, non-governmental organizations, often play a big role here too, advocating, educating, running programs on the ground. It takes a combination of approaches.
So technology plus awareness plus community action. A whole package deal. Okay, let's try and wrap this up. We've covered a lot of ground on current electricity.
We really have. From the basics of cells, primary versus secondary, chemical to electrical energy, to understanding current as the flow of charge, IQT, electrons versus conventional direction, the whole ampere definition.
Right, and the symbols. Learning that visual language for circuit cells, switches, resistors, rheostats, meters.
And how they connect series versus parallel and how circuits behave, like in that rheostat example.
Insulators versus conductors, based on those free electrons.
And the core concepts of potential difference, VWQ, as the push, measured in volts, And resistance, RVI, as the opposition, measured in ohms, Ohm's law tying it together.
Plus the factors affecting resistance material, length, area, temperature.
And finally, bringing it all home to the practical importance of energy efficiency, why it matters, how we achieve it with tech like LEDs and insulation, and the need for social awareness.
Yeah, for me, I think that rheostat explanation, visually picturing the flight or changing the length of the resistance wire in the circuit, that really clicked.
Ah, good. Seeing how it provides that continuous control.
Yeah, and just the sheer scale of potential energy savings from things like LEDs. It's not just small change, it's massive potential impact. Makes you think differently about flipping a switch.
Absolutely. And realizing these principles, current, voltage, resistance, are humming away inside basically every gadget you use.
From your toaster to your computer.
It connects the physics to everyday life. Understanding it, even at this level, helps you appreciate the tech, maybe make smarter choices about energy use. It demystifies things a bit.
Definitely. So as you, the listener, go about your day, maybe notice the things powered by electricity. Think about that invisible flow, the push from the source, the resistance in the components.
That constant dance of electrons.
Yeah, and maybe chew on this thought. We're hugely reliant on electricity, and that's only growing. Looking ahead, what completely new ways of generating, storing, or even using electricity might be just around the corner? What breakthroughs could change the game entirely?
That's a fascinating question to ponder. The field is always evolving.
It really is. Well, thanks for diving deep into current electricity with us today.